Thank you again for the great session we had earlier. I'll try to make it move quickly. Today, I'm from Kentucky. I'm going to tell you a superior, we call superior cell transfection device. What is for basically facilitating affordable gene-based cell therapy or cell-based gene therapy, whichever way you want it. Why gene therapy? Well, it's all about curing even the uncurable because of the limitation of our current treatments and medicine procedures and surgery, so on and so forth. Imagine that a 5-year-old girl with a leukemia with little hope to live and now celebrating her 11 years of cancer-free life. So the question is, why don't we do more? Well, the process is complicated. As you can see, in the case of a T cell, called T cell therapy, a T cell has to be extracted from the patient and then processed. In the case of a gene therapy, we typically use stem cell and things like that. And now you can see that in both cases, we have to deliver these gene modified molecules to basically into the cell. So this is the process called a cell transfection. So the issue is that this whole process is very complicated. That's why it's very costly. And so this is the problem we try to solve. So I want you pay attention to T cell, stem cell, and also currently we use virus for those intracellular delivery. So what is the problem we're targeting? The problem we're targeting is the adverse effect from those viral particles, and such as the other is very low efficiency in terms of T cells and stem cells. And also, alternatively, when people don't use a virus delivery, use physical means, and then these tend to cause more damage to both cells as well as the gene material. And then again, labor intensiveness in terms of cell preparation actually cause a lot of lower throughput issues, yields and efficiency, and even consistency. If you have even 20%, transfection efficiency, and not all the cell actually got the same amount of, so that and all leads to poor quality. And that leads, again, to very high cost. The cost actually now is between $400K to $3.5 million. This is why we cannot do more. And our solution is that we're going to provide a microfluidic-based technology with a much gentler way and healthier way to actually transfect cells. And what is the outcome? The outcome is we will achieve the highest possible transfection efficiency with consistency at individual cell level. And what that translates to is a high quality and high yields of all those cells. And then the platform is clock-free, high throughput. What does that mean? All cells for a single patient can be processed in a single run. And the device is very simple: single inlet, single outlet. And what does that mean? It means actually it will be operatable with a lower DC as well as a lower manual pressure under 1 bar at this case. So all these adds up to easy adoption and lower cost technology. So the question is, so this technology is actually built upon several IPs, and recently we have filed provisional patents on 3 of those. And as you can see here, one covers the technology directly applied to transfection, and then the other is the key component of the design of that, which leads to very impressive or unprecedented results. And then lastly, is also a technology that allow us to make those devices much cost effectively as well as precisely to deliver what we expect from the design. So then the question is, you probably wonder, show me the data. Well, here's the data. Science does deliver, as you can see. Even from a very preliminary study, we have already seen almost 100% transfection efficiency. And in this case, actually, the payload we actually use are typically about twice the size of a typical gene material. Now, How does that to put in perspective? Well, the same cells, the same conditions, typically this is what you'll get. By electroporation, you get about 6 to 70, and by lipid-based, you get 30. And these are, we're talking about commercial instruments and methods. So all these, again, is that you can see here by a very cost-effective devices and use 3D printing. Now, how do we compare in terms of other technology? Well, as you can see here, if I list all those, the key highlight I already mentioned earlier. So what is the market? Well, the market for gene therapy is actually already in the 15 and billions, and expect to grow to 80 some billions in about 10 years. Now, out of that number, about 80% actually belongs to cell acquisition, cell preparation, quality controls, and so on and so forth. So the technology actually has a lot to do with all of those issues. So that's why relevance is high. So our team actually is composed of two bioengineer and Dr. Tong, my engineering partner, is actually a more on the gene delivery, nano design, the nanomedicine side, and also Dr. Evans is a renowned physician. He runs the cancer center at University of Kentucky. So what is our next step? We actually are looking for collaboration to further evaluate and advance the technology. Particularly, we'd like to move on to more, we call the patient relevant cells and gene material. And then the second part, of course, is funding support to benchmark the technology on a much broader base. And finally, business investors to, help us to commercialize the technology. Thank you. I think we still have some time for me to answer a question if you guys, thanks again. You go first.
How many different cell types have you tested with this device?
Yeah, good question. We have so far tested two types of cells. And actually, one of those cells you mentioned, we also tested. So both cells gave us over higher than 95. Thank you.
Okay, but which cell types?
Oh, which cell types? Raw cell is one of them, which is basically a macrophage cell. And I think the other cell is, what is this? A Jerker cell, I think. Yeah.
And then what about the gene therapy part? Have you tried, so when you say, 2x the typical payload, can you just give me what that actually means numerically?
Yeah, okay, good. We'll have experts. so the payload we did is basically the nanoparticle conjugated with peptides. And those are the ones that my partner actually used for his gene therapy study, genetic medicine to deliver. So actually he saw some, of course, did not use the same method. He used kind of his lipids kind of way of delivering, but he saw the method, the particle, the cell actually saw a very impressive outcome. So yeah, but it's a different method.
Yeah, and just to give you context, my nosiness comes because, so I'm Tari Suprapta with Novo Nordisk, and we have both a cell therapy unit in Fremont, California, as well as an RNA and gene therapy unit, and with our acquisition of Dicerna, right? So, and that's going to be based in our soon to be completed R&D hub in Lexington, Massachusetts. And so I'm constantly looking at the space, and if you've made these types of breakthroughs, you are providing a very important solution to the problem. So I look forward to
thank you so much. I'll be looking for you to talk more.